Buffer overflows are one of the oldest and most commonly exploitable software vulnerabilities. They have existed for as long as there have been computer programs. They are also one of the most common software design and implementation errors. In fact, in some programming languages, it is very easy to make mistakes in writing software and firmware that cause illegal access to program memory, which is basically what a buffer overflow is. Fortunately, potential buffer overflow conditions are usually easy to find and fix, if you have the program source code, that is. So just what does a buffer overflow look like? Well, because buffer overflow conditions happen inside of computers, they are not easy to actually see. The effects of an overflow may be very noticeable by a change in your computer's behavior, but you can't see the overflow itself. The drinking glass overflowing with water is not a very accurate analogy either. The closest thing I could think of in real life is when you are filling out a paper form that contains tiny little boxes for writing your information in. If you have lots of information to write, such as a very long file name, it's really easy to run out of room and write past the end of the box into the next box, overflowing information to where it shouldn't be, as it were. If you think of the boxes on the form as buffers, and what you write in them as data, then you can visualize what's happening in a program's memory when a buffer overflow condition occurs. If you could see into the memory used by a running computer program, you would see many sequential memory elements that are used to store the program's data. We usually use a 1- or 2-dimensional grid to represent how these elements are organized. From this memory, the program creates buffers for storing the data used by the program. If you could see the actual data stored in a program's memory, and there are many tools that allow you to do this, you would see a world of nonsensical gibberish punctuated with numbers and characters, some of which may look familiar to you. Let's take a look at what a buffer overflow looks like from the buffer's perspective. Here we see a buffer allocated with 8 memory elements for storing 8 bytes of data. The elements are numbered 0 through 7 because, well, computers start counting at 0, so most programming languages do as well. The memory elements following the buffer might belong to another buffer, some other program, or maybe they're an unclaimed memory and not in use at the moment. All we know is those adjacent elements are not part of our 8-element buffer and are outside of our buffer's memory bounds. If we write the character string password into the buffer, we see that all of the data written into the buffer stayed within the buffer's memory space. However, if we were to write a longer string to the same sized buffer, the additional data would overwrite several of the memory elements adjacent to the buffer. This is exactly what a buffer overflow condition is. Another reason why the analogy of a buffer overflowing with data is like a drinking glass filling and overflowing with water is not entirely accurate is because of gravity. A glass must fill with water from the bottom up, but buffers in memory can have data written to them starting at any element. You can overflow a buffer by writing to only a few of its elements and not filling up the buffer at all. So when you see a buffer overflow occurs not because the buffer is full, but because the writing of the data to the buffer has overrun the memory boundaries of the buffer. This is why buffer overrun is a more accurate description for this condition. But it's the term buffer overflow that has stuck in modern cybersecurity speak. Common buffer overflows and overruns exceed the memory boundary at the end of the buffer. A related condition exceeds the memory boundaries at the beginning of the buffer. This is known as a buffer underflow or a buffer underrun. It may seem strange to fill a buffer with data starting from the end and proceeding backwards to the buffer's beginning, or filling from the bottom of the buffer to the top, depending upon your view, but in software design there are reasons to do this. And just with overflows and overruns, if you aren't careful where you are writing in the buffer and how many elements you are writing to, you could easily write past the beginning of the buffer, causing an underflow or underrun condition. One last point for me to harp on is that buffers are always writable and they are overflowed by writing data to them. However, it is also possible to exceed memory boundaries while reading from the buffer. This is not an overflow condition because no data is being written to memory locations where it shouldn't be. Attempting to read past the end of a buffer or prior to the beginning of a buffer can still be described as overrun or underrun conditions respectively. Be sure to note the detailed description of any exploit labeled as an overrun or underrun to check if it's writing or reading data in its operation. You might be surprised at the data you can find by just attempting to read places in program memory that are outside of, but close to, the boundaries of a buffer. Buffers aren't the only thing that can overflow. There is another condition called integer overflows that can also be exploited for nefarious purposes. However, buffer overflows and integer overflows are not the same thing, and you should understand why. Integers, or what we humans typically call number values, are stored in fixed-size areas of program memory referred to as variables, because the values can change. All integers are limited to a specific range of values based on the integer variable size, such as negative 32,768 or 32,767 for signed 16-bit numbers, and 0 to 255 for unsigned 8-bit integers. If we perform an arithmetic operation that exceeds the upper or lower size of the integer, and attempt to store the results in an integer variable that is too small, the value will roll over to the value on the other end of the integer's range. This condition is referred to as an integer overflow, although integer rollover might be a more accurate description. For example, adding 1 causes the largest integer value to roll over, or overflow, to its lowest value, like a car's odometer flipping over from all 9s to all 0s. Going in the opposite direction, subtracting 1 from the lowest value results in the highest integer value, which is sometimes called an integer underflow. It is the responsibility of the programmer who wrote the code to anticipate the possibility of integer overflow and underflow conditions and handle them accordingly. The two major problems that can occur with unhandled integer overflows are unexpected results from data calculations and unintended changes in program logic flow. These conditions can cause programs to return bad data and perform actions that are not intended by the program's designers. Many significant operational and security issues have resulted from integer overflows and underflows. Although buffer overflows and integer underflows are not directly related, one type of overflow can lead to another if an integer overflow condition results in the miscalculation of a buffer size, or a buffer overflow condition unexpectedly changes the value of an integer variable.